Hello everyone, myself Reddy Chakrapani and my friend Lokesh from Department of Physics. Today we are going to discuss about the topic crystal structure and symmetry in condensed matter physics. Table of contents. In this presentation we are going to discuss about the introduction to condensed matter physics, overview of crystal structure and the basic concepts and the types of lattices, symmetry in crystals and the Miller indices, and also the crystal systems, application of crystal structures, and their summary, and finally the conclusion.
So moving on to the introduction of condensed matter physics. What is condensed matter physics? In this introduction slide, we are discussing that condensed matter physics is the study of matter in a condensed phases, which is like, for example, solids and liquids. It focuses on their physical properties, emphasizing their orderly arrangements or lack thereof, like whether it's a crystalline or amorphous structure. And why it is so important? It's a basis for modern technologies, for example, semiconductors, superconductors, and this condensed matter physics explains phenomena like phase transitions and quantum effects. The key topics which we'll be discussing in this condensed matter physics is it's about structure in the sense like whether it's a crystalline material or it's a amorphous material, and the properties of the materials, electronic, magnetic properties, and its thermal behaviors. And well, like delving deeper, we'll more look into the quantum phenomena, that superconductivity and Bose-Einstein condensates. But in this particular presentation, we are not looking into this.
Crystal structure. What is crystal structure? It is an unique arrangement of atoms, ions, or molecules in a crystalline solid, which is characterized by its periodic or repeating pattern. This orderly organizing extends throughout the material and significantly influences its physical and chemical properties. Crystals, they are solids where the constituent particles like atoms, ions, or molecules that are arranged in a highly order, maybe in a repeating 3D pattern. This distinguishes the crystalline solids from amorphous solids, which lacks the long range order. And basic concept. Lattices. It is a periodic array of points in space representing the atom positions. In this figure, we can see that an unit cell. It is a smallest repeating unit that defines the entire structure, that defines the entire crystal structure. Symmetry. That includes the symmetry, which includes the translational and rotational and the reflection symmetry. In simple cubic, the atoms are at a corner of the cube, whereas in body-centered cubic, atoms are at corner and also at one at the center. And in face-centered cubic, the atoms are placed at the corner and also one at each center. Whereas in hexagonal, it is an hexagonal layer of atoms. Types of lattices. There are 7 unique arrangement of unit cells. Uh, they are simple cubic, tetragonal, orthorhombo, orthorhombic, and monoclinic, triclinic, hexagonal, and rhombohedral. And in simple cubic, the angle is like alpha is equal to beta is equal to gamma. It is 90 degrees, whereas A is equal to B is equal to C. Whereas in tetragonal, the A is equal to B, but B is not equal to C. Whereas the angle between the alpha, beta, gamma, it is equal to 90 degrees. Whereas in orthorhombic, A is not equal to B, and B is not equal to C. But the angle between the alpha, beta, and gamma, it is equal to 90 degrees. Whereas in rhombohedral, the angle between alpha, beta, gamma are 90 degrees, and also A is equal to B is equal to C. Whereas in monoclinic, A is not equal to B and B is not equal to C. And the angle is alpha equal to gamma and it is equal to 90 degrees, whereas beta is not equal to 90 degrees. In triclinic, A is not equal to B and B is not equal to C, and the angle between the alpha, beta, gamma, it is not equal to C. Whereas in hexagonal, A is equal to B, but B is not equal to C. Whereas the angle between alpha and beta, it's 90 degrees, but in gamma, it is 120 degrees. In 2D Bravish lattices, there are four types of 2D Bravish lattices: square, rectangle, rectangular, hexagonal, and oblique. In 3D Bravish lattices, there are 7 unit cells which are characterized into 14 Bravish lattices. There are cubic, rectagonal. These 7 unit cells are classified into 14 Bravish lattices. And also the in cubic we can see it is characterized into primitive, body centered, and face centered, whereas in pentagonal it is only primitive and body centered, whereas in orthorhombic it has the all like primitive, base centered, and body centered, and uh, face centered. Symmetry in crystal. Symmetry. It is an operation that maps a crystal onto itself. The types of symmetrics are that previously we discussed that transitional, rotational, mirror, and inversion. Transitional means it is the repeating pattern at a regular intervals in 3D space, whereas in rotational, it rotates around the axis. That leaves the crystal looking like the same. For example, the 2D fold and the 3D fold. And in mirror, it is a mirror half of crystal uh, across the plane. And in inversion, every point is reflected through the center, producing an inverted pattern.
In the previous slide, we discussed about what are the types of symmetry. So now we'll delve deeper into it. Like we'll separately see what are different types of symmetry. So first we'll move on to translational symmetry. Translational symmetry, it refers to the repetition of unit cell or a pattern at regular intervals in a specific direction, which will be throughout a crystal lattice. And it ensures that structures appears identical when shifted. That means if it translated by a vector corresponding to lattice parameters. This periodicity is defining feature of crystalline materials. If we consider an unit cell, which is like if you consider a crystal structure, you can see from the picture, it's an hexagonal unit cell. You can consider this as hexagonal unit cell, and this hexagonal unit cell is translated into 3 different points with some different in directional vector. It vector continuously changes if you're doing translational symmetry, whereas in other symmetries, no, it will, its position, everything will be changed, but you can see that same structure is formed. This is like repeating pattern, because most of the crystal structures are having translation symmetry with the continuous repetition pattern, which was described here. It refers to the repetition of unit cell or a pattern. So next we move on to point group symmetry. It describes the set of symmetry operations such as rotations, reflection, inversion, and roto-inversion that leave at least one point in a crystal fixed while mapping the structure onto itself. Which means, like, if we consider one unit cell or a crystal structure, we'll just fix one particular point, and whatever symmetry is going on to through that crystal, which all comes under point group symmetry. These symmetries define the external shape of a crystals and are categorized into 32 point group symmetries, which are grouped under the 7 crystal system. Previously, we studied about 7 crystal system. So these 7 crystal system are classified into 32 point group symmetries. Point groups are very critical for determining optical and mechanical and physical properties of a material. Like for a research purpose, this point group symmetry like inversion, if all point groups, studying this point group symmetry will be very handy. So in a picture you can see like this is an unit cell. You can consider this as a unit cell. This is a center point, this is a fixed point where rotation takes place. It's a circular thing which has four quadrants, starts from 0 degree to 360 degree. So this more number of like few major examples of this point group symmetry we'll see in the future slides. Now we'll move on to rotational symmetry. This refers to the ability of a crystal to look identical after being rotated around an axis by specific angles. The number of times the structure matches itself in a full 360 rotation defines the order of symmetry. Example, we can call it as twofold if it moves in 180 degree, or threefold if it's like if we are rotating in 120 degree. Allowed rotation in crystals are restricted to one fold, two fold, three fold, four fold, and six fold due to periodicity of crystal lattice. So in picture you can see like in the rotational symmetry, this atom is at E position. That's its initial position. When we turn into 90 degree, no, the atom comes here. So it's a 90 degree turn. And again, we are doing another 90 degree turn. So it will be totally 180 degree. The atom moves to other position. When we do 270 degree, the atom is at another position. And finally, atoms returns to its original position when we move 360 degree. This is an like one type of fold symmetry where like full 360 degree rotation gives the initial position of the atom. In the mirror symmetry, it occurs when crystal structure is divided by an imaginary plane such that one of is the exact mirror image of other. These mirror planes can be oriented into various directions and are fundamental element in classifying crystal structure and their symmetry. So like see, you can see some shapes where this you can consider as a mirror line. Each shape, no, it is like reflecting the exact image of the same shape. This is called mirror symmetry. This sometimes, no, these mirror planes are like imaginary planes. You should consider that like if one crystal structure is forming the exact same structure in the other side, no, which will be like vertically opposite to each other. This is called mirror symmetry. So now we'll move on to inversion symmetry. Inversion symmetry is one critical symmetry which we'll be discussing. It occurs when every point in a crystal can be mapped to an equivalent point on the opposite side of a center of symmetry. That we call it as inversion point, such that its structure remains unchanged. So you can see from the picture. So this portion, 1, 2, 3, 4, and 5, 6 portions. These portions are like center of inversion is there, which is shown by some green color atom. So the same inversion, while after doing the inversion, no, nothing has changed, but its position, like you can see from the coordinates, initially it was like XYZ coordinates, and these XYZ coordinates are transformed into minus X, minus Y, and minus Z. This is called inversion symmetry.
Space group and its examples. What is space groups? It describes the full symmetry of a crystal structures, which is combining of the point group symmetry with the translational symmetry. That means the lattice translation, grid planes, and screw axis. There are 230 unique space groups in 3D, which are characterized based on the uh, systems, and they provide as a comprehensive mathematical framework for understanding the arrangement of atoms in a crystalline materials. Trigonal system, which is seen in ferroelectric materials like lithium niobate and arthrium, which is found in quartz. Monoclinic system, which is found in many silicate materials like gypsum, and P21 by C, which is common in organic crystals and pharmaceutical. Examples of space group in cubic systems, the face-centered cubic, which is mainly found in materials like gold and aluminium, and in I3 IM3M, which is body-centered cubic, which is mainly found in iron and tungsten. In tetrahedral systems, P4mm, which exhibits the simple tetrahedral symmetric, which is common in the ferroelectric materials like barium titanate, and I4 by MMM, which is found in certain alloys and materials like rutile. Orthohombic systems, uh, it is common in many inorganic components like olivine minerals, and CMCM, which is seen in layered materials like graphite intercalates. And in hexagonal systems, uh, P63 by mmc, which is found in magnesium and zinc, whereas P6 by mm, which is characterizes its ideal hexagonal closed packed structures. In triclinic systems, P1, it is the simplest space group with no symmetric beyond the translations. And in P-1, which accepts the inversion symmetric found in materials like potassium hydrogen phthalate.
So now moving on to Miller indices. Miller indices are a set of three integers which are denoted by H, K, and L that represent the orientation of crystallographic plane in a crystal lattice. They are widely used in crystallography to describe specific direction and planes in crystal. So now we'll see like how to determine this Miller indices. Before that, no, like what is Miller indices? It's a notation system used in crystallography to describe the orientation of plane or set of parallel planes of atoms in a crystal. The purpose of Miller indices are used to uniquely identify a plane or surface and to understand phenomena in material science. So to study, like to determine the Miller indices, first we have to identify the intercepts of the plane with crystal axis in terms of lattice constant, which can be like A, B, C, A, B. So it's a arrangement of atoms. And with these intercepts, we'll just take the reciprocal of these intercepts. This is the second point in the determination of Miller indices. And by clearing the fractions by multiplying the least common multiple, that is, if we take LCM and if we express it as in integers, we'll get the Miller indices. So how this Miller indices can be represented? For example, like I already told, like Miller indices is a set of three integers which will be denoted by HKL, and each HKL denotes a specific crystallographic plane. And sometimes no, UVW also denotes a direction in the crystal. Some HKL denotes a family of equivalent planes due to symmetry. Because like if we take crystal structures, we have many number of planes. Each planes will be explained by this Miller indices. Now we'll see examples of Miller indices. Simple plane. So the description for the simple plane is the plane intercepts the x-axis at some position A, and it's parallel to y1 z-axis. Examples: in a cubic lattice, this represents one of the faces of the cubic. And in the next, we call it as diagonal plane, which will be like 110, and its description is the plane intercepts the position x and y axis at A and B point respectively, which will be parallel to the z-axis. It represents the diagonal face of a cubic crystal, and it's a triangular plane. So in triangular plane, which will be like triple one plane, it's like one of the major planes for the research purpose. Like we use most of the crystal structure in this triple one plane. The plane intercepts x, y, and z axis at A, B, and C respectively. It is majorly found in face-centered cubic structures such as slip plates in aluminum. So you can see a picture. For 100 plane, the plane intercepts the x-axis and at A point. So which is like it forms a simple plane. In diagonal plane, it intercepts the x-axis and y-axis at A point and B point. And in the triangular plane, it intercepts x-axis, y-axis, and z-axis at A and B and C position respectively. So moving on to some more examples of Miller indices, that is higher index plane, which we call it as 200 plane, a plane parallel to 10 but closer due to intercepting at A by 2, A by 2, A by 2 on the x-axis. Example, it is majorly observed in the higher order diffraction peaks. And that is, now we'll move on to top bottom plane. The plane intercepts the z-axis at C point and is parallel to x and y axis. Represents the top or bottom face of a crystal in a cubic system. Now mixed plane, which we call it as 101 plane. Description: the plane intercepts the x-axis at A point, z-axis at C point, and is parallel to y-axis. Represents the tilted plane within the crystal lattice. So you can see a 200 plane there. So like the how the plane is as some intercepts, and 001 plane and 101 plane.
The next is crystal systems. What is crystal systems? It is a classification based on the symmetry and the geometry of crystal unit cells, particularly the length of its edges and the angle between them. There are 7 crystal systems in total, with each distinct features and defined by the arrangement of atoms, ions, or molecules with the crystals. And the application of crystal systems are understanding the crystal system helps in predicting the behavior of materials by which includes the mechanical, optical, and electrical properties. And these are crucial for various industries like electronic, pharmaceutical, and the material science. Cubic crystal systems. Uh, the cubic crystal systems, it is one of the 7 crystal systems, and which is characterized by 3 equal axes that are at 90 degrees to each other. It has the highest symmetric and is most symmetric of all the crystal system. The representing the unit of crystal in unit cell, which is in case of cubic system is a cube. There are 3 main types of cubic lattices with different arrangement of atoms. First is simple cubic. Simple cubic, it is the simple cubic. It is defined as the atoms are located at the corner of the cube, and each atom in the corner is shared between the 8 unit cells by giving the efficiency about 52%. For example, polonium. And in BCC, body-centered cubic, the atoms are placed at the corner, and one atom at the center of the cube. This arrangement increases the packaging efficiency to 68%. Example, ion at room temperature. And FCC, face-centered cubic. Atoms are located at the corner and the center of each face of the cube. This arrangement has the highest packaging efficiency of about 74%. Example, aluminium, copper, gold. Face-centered cubic and body-centered cubic structures. Um, Properties: number of atoms per unit cell. In FCC, there are 4 number of atoms per unit cell, whereas in BCC, it is 2 number of atoms per unit cell. And packaging efficiency, as we discussed, the FCC has the highest packaging efficiency of 74%, whereas in body-centered cubic, it is up to 68%. And the slip system, it is like FCC, it is 12, which is more ductile, and in BCC, it is 6, which means more brittle at low temperatures. Ductility. The FCC has the high ductility, which is easily deformed, which can be easily deformed, whereas in BCC it is low ductile, which means more prone to brittle fracture. The strength of FCC, it is moderate at high temperature, whereas in BCC it has high strength at elevated temperature. The common metals in FCC are aluminum, copper, gold, and silver. And the common material for body-centered cubic are iron, chromium, tungsten. And the temperature sensitivity of FCC is less sensitivity to temperature changes, whereas in body-centered cubic it is stronger at high temperature but more brittle at low temperature. In this figure, we can see that the FCC and the BCC, there are and here we can see that six faces at the center in FCC, and here one atom at the center of the cube, and there are eight corner positions, same as in BCC.
So now we'll move on to hexagonal close packing structure. And it is one of the common atomic arrangements found in crystalline solids where atoms are arranged in a tightly packed structure. The HCP structure is characterized by a specific arrangement of atoms that provides high packing efficiency. It has consist of two types of layer. First layer is hexagonal arrangement with the atom positioned at corners of an hexagon and one atoms at the center. The second layer B, which we usually call, is positioned in the gaps above the atoms in the first layer. The atoms in the second layer sit directly above the gaps formed by the first layer, creating AB pattern. That will be like a repeating pattern AB, and which is called as SCP structure that repeats throughout the crystal. So you can see a picture of a close hexagonal close pack structure. The first atom A arrangement has six atom, which is like hexagonal arrangement, and B as a portion in the gaps. So these, which like the cursor is moving now, which are like B portion atoms. So usually it forms AB patterns. Now we'll move on to coordination number. Coordination number refers to the number of nearest neighbor atoms or ions surrounding a central atom or ion in a crystal structure. It is measure of how many atoms directly touch a given atom in the solid. Like in the previously in many slides, we have seen the crystal arrangements. Each crystal has a different and unique arrangements. And in that, no, like different atoms will have a connection with many other atoms. This will be explained by this coordination number. It is measure of how many atoms directly touch a given atoms, as I said earlier. And this coordination number plays a major role in determining the stability, packing efficiency, and the other physical properties of a material. So, how to determine this coordination number? So, let's take an example. We consider this FCC as a structure, and we'll just see like how the coordination number for this FCC structure can be found. The coordination number is determined by the arrangement of atoms within the crystal structure, which we already discussed, and is influenced by the geometry of the unit cell. In general, coordination number increases as the packing efficiency of crystal increases, as atoms are more tightly packed together. So you can consider, like if we consider the central atom will have a coordination number of 12 atoms. See, like each as no, like in the top layer we have four different atoms, and in the bottom layer we have four different atoms, and in the central region we have four different. So this particular atom, no, which has coordination number as 12, because it has connection with 12 different atoms, so we call it as this as coordination number.
Atomic packaging factor, APF. It is a measure of how efficiently the atoms are packed in a crystal structure. It can be like the formula of APF is the volume of unit cell that is occupied by the atoms, indicating how tightly the atoms are packed. APF is equal to the volume of packed by atoms in unit cell by volume of the unit cell. The APF of simple cubic is 0.52, and the FCC is 0.68, and the body-centered cubic is 0.74, and the hexagonal closed packing is 0.74. The comparison of crystal structures. Let's compare the let's see the simple cubic, body-centered, FCC, and hexagonal closed package and the dimensions. These are the properties. Like in simple cubic, the atoms per unit cell is 1, in BCC it is 2, whereas in FCC it is 4, and hexagonal closed package it is 6, and the diamond cubic is 8, whereas the packaging efficiency for simple cubic it is low, and it is similar and it is same for the diamond cubic, whereas FCC and hexagonal package it is high, the packaging efficiency is high, whereas in BCC it is moderated. Example of simple cubic is polonium, whereas body-centered cubic it is iron, and face-centered cubic is aluminum, and hexagonal it is magnesium, and the diamond cubic it is diamond. Uh,
So now we'll move on to the XRD. So XRD is one of the non-destructive technique, and it's a very powerful technique to study determine the crystal structures of the materials. So it majorly works by directing X-ray onto a crystalline sample and measuring the angles and intensities of the diffracted beams. So you can see the sample stage. So X-ray source will be here, and it will like continuously emit X-rays onto the sample. And this refraction, no, like after refraction, it will just we can just X-ray detector will be there, which will detect the X-rays after refraction. The resulting pattern provides the information about the arrangements of atoms in the crystal, including its universal dimension, crystal symmetry, atomic positions, and phase identification. And with this, no, with this phase identification, we can see like how to determine what materials are present in a sample. So this XRD majorly works through Bragg's law, which relates the angles at which X-rays are diffracted by a crystalline material to the spacing between its atomic planes. It is given by the equation n lambda equal to 2d sine theta, where n is order of diffraction, usually 1 for first order diffraction, and lambda is the wavelength of incident X-rays which will be injected on the sample. D is the distance between the crystal plane, which we call it as D spacing, and theta is the angle of incidence, that this Bragg's angle. So you can see from the picture, X-rays are injected onto the sample, that is a crystalline structure. So this crystalline material X-rays are injected, and after refraction, no, we can just analyze the refracted rays through X-ray detector.
the applications of crystal structures. The first one is material design and engineering. Determining the mechanical properties such as strength, hardness, and ductility, then influencing the design of alloys and the composites. In semiconductor industries, it is a crucial for the properties of materials like silicon, that is used for the transistors and solar cells. And X-ray crystallography, which is used to determine the 3D structures of biomolecules and materials. Uh, Catalysis, crystal structures influencing the efficiency of catalysts, efficiency in chemical reactions used in petrochemical and environmental industries. And in nanotechnology, this crystal structure of nanomaterials determine their unique properties, enabling the application in sensors, electronics, and the drug delivery. Defects in crystals.
So there are many number of types of defects in crystal. So we'll see like one by one. First, we'll see point defects. In point defects, we have three different types, that is vacancy, interstitial, and substitutional. In vacancy, atom will be missing, whereas in interstitial, extra atom will be present in a lattice, and in substitutional, foreign atoms replaces the original atom. And if we move on to line defects, that is dislocations, sometimes edge of the crystal structure will be dislocated. That is like we can it will be like adding extra plane of atoms. And so it is another thing is screw dislocation, where spiral shift of atoms takes place. And in the third defect, no, we see it as surface defects, which will be like categorized into two. One is grain boundaries and stacking faults. So grain boundaries are it's a boundaries between crystallites, whereas in stacking faults it's a misalignment of atomic planes. And in volume defects majorly sees about the porosity, which is voids in the crystal or some vacant space in the crystal, and inclusions, foreign particle will be present inside the crystal. And impurity defects, it's like alloying or doping, that is adding a foreign atoms to alter its properties. So you can see various defects, point defects of a crystal. In the vacancy defect, one atoms is completely missing from the crystalline structure, whereas in interstitial impurity, one impurity is like added or it is doped into it. And self interstitial is like the atoms structure will be like different from other things from its serial patterns. Substitution impurity is like replacing an foreign atom with the original atom, and we have Frenkel defects, Scotty defects, like that.
And the significance of symmetry. The property prediction, like symmetry helps to predict the materials physically. Example, the strength and conductivity, and chemically, example, reactivity, catalysis properties. And the classification, the symmetry aids in classifying the crystals into different space groups and the crystal systems, which simplifies the structural analysis. And the X-ray diffraction, the symmetry simplifies the interpretation of X-ray diffraction pattern and aiding in the determination of crystal structures. And the mechanical behavior is it influences the ductility and the strength of materials by affecting the dislocation, movement, and the slip systems. And the defect formation, the symmetry affects the behavior of defects in crystals and how they propagate.
So finally, we conclude this presentation. Crystal structure and symmetries play a crucial role in material science, electronics, and physics. So in recent research and advancement in material science, studying about crystals will create a huge impact in your analysis. The study of crystal structure and symmetry bridges theoretical and applied sciences, offering a deep understanding of material properties and enabling the development of novel technologies. In essence, crystal structure and symmetry are foundational to a wide range of industries and research fields, enabling innovations and optimization of material properties. So, overall, this crystal structure analysis will help for researchers in the future to study about its properties. So, thank you for the attention. Thank you so much.
Pause, stop.